Hi, I'm Bob. Welcome back to the Econometric tutorial on basic concepts and series. In econometric analysis, we often use matrices to show the regression models and the properties of the estimators. Today, I want to introduce some basic matrix concepts, operations, and properties that can help you better understand the advanced courses in econometric analysis. A matrix is a particular arrangement of numbers. The horizontal lines of numbers form rows, and the vertical lines of numbers form columns. A matrix with m rows and n columns is said to be an m by n matrix. We can write a matrix with its entries as follows. The subscripts of the entries indicate their positions. For example, matrix A is a 4 by 5 matrix. The entry A23 means the number is in the second row and the third column. The transpose of the matrix A is a 5 by 4 matrix. It is denoted by A' or AT. It is obtained by interchanging rows and columns. The transpose of a 1 by 1 matrix or number is itself. Here are 5 properties of matrix transpose. The third property means the transpose of the product of two matrices equals the product of two matrix transposes where the order is changed. The fourth property means we can swap the operations of transpose and inverse and have the same result. A square matrix is a matrix with m equals n. It has the same number of rows and columns. A symmetric matrix is a square matrix, and its transpose equals itself. An idempotent matrix is a square matrix. The matrix A is said to be an idempotent matrix if and only if A multiplied by A equals A. Finally, an m by 1 matrix is a column vector, while a 1 by n matrix is a row vector. Let's look at some examples. In the regression model of y equals x times beta plus epsilon, the outcome variable y is an n by 1 column vector. It contains entries from y1 to yn. The error term epsilon is also an n by 1 column vector containing elements from epsilon 1 to epsilon n. The explanatory variable matrix X is an n by k plus 1 matrix if the model has an intercept and k explanatory variables. The population parameter beta is a k plus 1 by 1 vector. In econometric analysis, we often encounter some particular matrices. The first one is x prime times x. X is an n by k plus 1 matrix. Its transpose is a k plus 1 by n matrix. So x prime times x is a k plus 1 by k plus 1 square matrix. It is a symmetric matrix because its transpose equals itself. The second useful matrix is the projection matrix Px. It gets its name because when Px pre-multiplies the outcome variable y, the result is the projection of y on the x space, namely y hat. We can show that the projection matrix is symmetric and idempotent. The third matrix we will see in econometric analysis is the residual maker Mx. It is also constructed by X. Like the projection matrix, the residual maker is symmetric and idempotent. Next, I want to introduce the matrix trace. Suppose A is an n by n square matrix. The matrix trace is the sum of the diagonal elements. It is a number. Notice that for a 1 by 1 matrix C, the trace is itself. A 1 by 1 matrix is a number or scalar. The properties of the matrix trace are as follows. The third property is sometimes called the permutation rule. The trace is invariant under cyclical permutation. The fourth property states that the trace of a matrix equals the trace of the transpose of that matrix. Next, let me introduce the determinant of a matrix. The determinant of a matrix is a number. For a 2 by 2 matrix, we have a formula for the determinant. The next concept is the matrix inverse. Let A and X be n by n matrices. If A multiplied by X equals the identity matrix I, then X is the inverse of A, denoted by A to the power minus 1. If the inverse of a matrix A exists, it has the same dimensions as A. We have the formula for the inverse of a 2 by 2 matrix. Swap the positions of A and D. Put negatives in front of B and C, and divide everything by the determinant of A. We use the matrix inverse in the computation of the OLS estimators. The minimization of the residual sum of squares leads to the normal equation. We pre-multiply the inverse of x prime times x on both sides to obtain the OLS estimator vector B. Here are the properties of invertible matrices. The matrix inverse is related to the matrix determinant in this way. A matrix A is invertible if and only if its determinant does not equal 0. Next, we will have a look at the concepts of eigenvalues and eigenvectors. Let A be an n by n matrix, X a non-zero n by 1 column vector, and lambda a scalar. If A multiplied by X equals lambda multiplied by X, then X is an eigenvector of A, and lambda is an eigenvalue of A. The eigenvalue is also called the characteristic root of A because the eigenvalue and the eigenvector form a special pair that reveals the characteristics of the matrix A. To find the eigenvalues of a matrix A, we construct the characteristic polynomial of A, set it to 0, and then solve for lambda. The following are the properties of the eigenvalues of a matrix and how the eigenvalues are related to the inverse of the matrix, the transpose of the matrix, the trace of the matrix, and the determinant of the matrix. First, if lambda is an eigenvalue of A, then 1 over lambda is an eigenvalue of the inverse of A. Second, if lambda is an eigenvalue of A, then lambda is also an eigenvalue of the transpose of A. Third, the sum of the eigenvalues of a matrix A equals the trace of the matrix. Fourth, the product of the eigenvalues of a matrix A equals the determinant of the matrix. We have learned some basic operations of a matrix, like the transpose of a matrix and the inverse of a matrix. We also touch on some fundamental concepts and properties of the matrix, including the trace of the matrix, the determinant of the matrix, and the eigenvalue of the matrix. These concepts are interrelated and form the basics of matrix algebra. We will use them in the advanced courses on econometric analysis. Thank you for watching this video. See you soon. Bye. Thank you for watching this video and subscribing to my YouTube channel. See you next time.